Hello guys, welcome to Victor Science Hub. In today's video, we're talking about mathematical induction. Mathematical induction is a proven technique that is used to show that a statement is true for all natural numbers. Now, when we say natural numbers, we mean numbers from 1, 2, 3, 4, 5, 6 up to infinity. Natural numbers are a set of positive integers starting from 1 to infinity. So what mathematical induction is for is just to prove that the statement works for all the natural numbers. Now, when do we use mathematical induction? We use mathematical induction when the statement has a pattern. So when there is a pattern in the statement, we use mathematical induction. We also use mathematical induction when the statement involves natural numbers. We also use mathematical induction when the statement applies to all natural numbers. That means mathematical induction should work for all the natural numbers, not only one or two natural numbers. It should work for all of them. Now let's go into the theorem of mathematical induction. The theorem of mathematical induction applies to a statement. Let's call the statement P of n, where n is an element of the natural number. That is, n is a natural number. So we prove that this statement is true by first testing that P of 1. When we test that P of 1 is true, the second step that we follow is that we now assume that P of k is true where k is greater than or equal to 1. So the first thing, when we want to prove a statement using mathematical induction, the first thing we have to do is that we test that statement for 1. So if 1 is true, the next thing that we are going to do, we are going to assume that P of k is true. So when we assume that P of k is true, we now prove that P of k plus 1 satisfies the statement. Then when we prove that P of k plus 1 satisfies the statement, that means that mathematical induction is true. That is true for all the natural numbers. So now let's solve one example. We have this problem. It says prove the mathematical induction that 1 plus 2 plus 3 plus ... plus n is equal to n into n plus 1 over 2, where n is an element of the natural number. So solution. Now, when we are proving mathematical induction, the first thing we have to do is to prove that P of 1 is true. We first have to test for P of 1. So first, we check for the left-hand side. So n is equal to 1 for the left-hand side. Then for the right-hand side, we have, this is for the left-hand side. While for the right-hand side, we have n into n plus 1 over 2. Then we put n to be 1. So we have 1 into 1 plus 1 over 2. That is 1 into 2 over 2. That is 2 over 2, which is 1. So the right hand side is equal to the left hand side. So therefore, P of 1 is 2. So now we have tested for P of 1. and P of 1 is 2. Now we go to the next one. So since P of 1 is 2, we are going to assume that P of k is also 2. So assume P of k is 2. Assume P of k is 2. Then we are now going to go to P of k plus 1. So what is P of k? So we have 1 plus 2 plus 3 plus dot 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 plus k is equal to k into k plus 1 over 2. So what I just did is that since it's P of k, anywhere I saw n, I put k. So this is for P of k. So we now test for P of k plus 1. So P of k plus 1 is what? After k, we have k plus 1. So what we are just going to do is that we are going to put all of this and add k plus 1 to it. So we have 1 plus 2 plus 3 plus dot 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 plus k plus k plus 1 is equal to, now anywhere we see n here, we are going to put k plus 1. So we have k plus 1 into k plus 1 plus 1 all over 2. We assume that 1 plus 2 plus 3 plus dot 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 plus k is equal to this. Since we have assumed this, that means this is equal to this value. So what we are just going to do is that this value, we are going to put it as k into k plus 1 all over 2. So we have k into k plus 1 all over 2 is plus k plus 1 is equal to k plus 1 into k plus 2 all over 2. K times k plus 1 is what? K square plus k all over 2 plus k plus 1 is equal to, now let's open the bracket for this one. We are going to open the bracket, we'll multiply k times k, which is k square, and k times 2 plus 2k, 1 times k plus k, 1 times 2 is 2. So now the next thing we are going to do is that we are going to take the LCM for this. LCM of this is 2. So 2 goes here is 1. 1 times this is k square plus k plus 2 goes here is 2. 2 times k plus 1 is 2 into k plus 1 is equal to this plus this, collecting like times this plus this is 3k. So we'll be having k square plus 3k plus 2 all over 2. So now, opening the bracket, we have k square plus k plus 2k plus 2. 2k, 2 times k, 2k, 2 times 1, 2 all over 2 is equal to k square plus 3k plus 2 all over 2. So this plus this is k square plus 3k plus 2 all over 2 is equal to k square plus 3k plus 2 all over 2. Now you can see that they are equal. Now we have been able to prove that p into k plus 1 is 2. Since p into k plus 1 is 2, that means this statement satisfies all natural numbers. It works for all natural numbers. So we are going to say, therefore, p of k plus 1 is 2. That means then p of n is 2 for all n element of a natural number. So what this statement is just saying is that since p of k plus 1 is 2, then p of n is all natural numbers. P of n is 2 for all n equal to a natural number. So we have been able to prove that this statement is true for all natural numbers. Now we are going to go to the next question. For all n is an element of the natural number. So remember, to solve a mathematical induction question, you have to start with P of 1. We'll check if P of 1 is true. The solution for P of 1, n is equal to 1 for the left hand side. So n is equal to 1 for the left hand side. Then for the right hand side, we have n square. So n square is equal to 1 square. That is equal to 1. So therefore, P of 1 is 2. So P of 1 is 2. Now the next step is to assume that P of k is 2. So assume P of k is 2. Assume P of k is 2. That means what we are just going to do here is that we are going to put k since it's P of k. So we have 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 is equal to k square. So the next thing, we are now going to prove that P of k plus 1 is 2. We prove that P of k plus 1 is 2. Now, for P of k plus 1, after k is k plus 1. So, what we are just going to do is that we'll put this 1 and add k plus 1. But since the equation is not since this expression is not direct, what we are just going to do is that when we have added this whole one, we are now going to do plus 2 into k plus 1 minus 1. So I'll show you what I mean. So after k plus 1 is the number after k. So we are going to have 1 plus 3 plus 5 plus dot 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 plus 2k minus 1 plus 2 into k plus 1 minus 1 is equal to k plus 1 all squared. The next thing is, since this is equal to this, we have already assumed that P of k is 2 and this is equal to this. That means anywhere we see this value, we are just going to put k square because this value is equal to this. So we have k square into 2 times k is 2k. 2 times 1 is 2 plus 2 minus 1 is equal to k plus 1 all squared. So we'll be having, okay, yes, it's supposed to be k square plus, so we'll be having k square plus 2k plus 2 minus 1 is equal to k plus 1 all squared. So that is k square plus 2k plus 1 is equal to, expanding this is k plus 1, k plus 1. So we have k square plus 2k plus 1 is equal to expand this, we'll multiply this and this, which is k square. K times 1 is plus k, 1 times k is plus k, 1 times 1 is plus 1. So k square plus 2k plus 1 is equal to k square plus 2k plus 1. Now we have been able to prove that the left hand side is equal to the right hand side. That means P of k plus 1 is 2. So since P of k plus 1 is 2, this statement is going to work for all natural numbers. Therefore, P of k plus 1 is 2. Then P of n is 2. for all. This is another way of writing for all instead of just writing for all. This is the symbol for all. N is equal to a natural number. Is an element of a natural number. So we have been able to prove that this statement is true for all natural numbers.